So our time is limited, and we have a lot of valuable insights to share. So allow me to jump to introducing today's speaker, Roy Cross. Roy is an ASME Y14.5-2009 GD&T Senior Level Certified Professional. He has experience in the application of GD&T dating back to 1978 as a designer, checker, and design leader. As a dimensional engineer, he's performed dimensional analysis and approved gauges, inspection fixtures, and measurement plans. He's a key member of SAE's GD&T content development team and has been teaching GD&T since 1991. Roy will spend the next 50 minutes providing you with a detailed overview, after which he will entertain questions. And I thought I'd mention that you may submit questions at any time during the webinar by typing your question into the Ask a Question box located to the left-hand side of the presentation slides. You can simply type your question in the box and click Send. And with that, Roy, I'll turn the program over to you.
Thank you, Sam. Good morning, everybody. It's good to be here with all of you. I'm hoping you're having a great day also. And it's my desire that the information I share with you will help expand your knowledge of GD&T and reinvigorate your passion for GD&T. Okay. So first, we'll discuss general changes to the 2018 version of the standard, and then we'll provide an overview of some of the more significant changes to the first three sections of the standard. Okay. One of the significant changes is reorganization of the content itself to help improve clarity and to conform to the Y14 series conventions. A couple of the geometric symbols have been removed that were not often used in industry and oftentimes provided confusion within industry. We'll talk about those. And then there were a few things that were added. In many of the figures, there were 3D model applications added to address current industry practices. There were a couple modifying symbols added to address practical applications in industry. And there were several clarifications, first one being direct plus-minus tolerance versus geometric tolerance applications. Some of the existing geometric symbol definitions, tolerance zones, and requirements were also clarified. And also in the Datum reference section, there's several terms and requirements that were clarified. And last, there were many non-technical edits to address inconsistencies within the standard. So let's start with the first three sections. Okay. In the previous version of the standard, 2009, the first three sections consisted of the scope, references, definitions, fundamental rules, general tolerancing and related principles, and symbology. And in 2018, the first three sections are just focused on scope, references, and definitions. And this will be the same for all Y14 standards as they are released or updated. So let's start with section 1. Again, per the Y14 conventions, it's going to just address introduction as well as general format description and reference to the Y14.5 standard, which is mandatory on drawings. And then what's new is the ASME Y14 series format conventions. That is explained in this section. And also new is addressing drawings without reference to a standard. So we'll mention that to talk a little bit about that. Reference to gauging for explanatory purposes only is not new, and that's still part of section 1. Okay, so let's talk a little bit about the Y14 series conventions. So in section 1.4, it addresses mandatory, recommended, guidance, and optional words and phrases. And then 1.4.2 addresses cross-reference to other standards and explains dated versus non-dated reference of standards. And then invocation of reference standards is also explained in terms of, when an entire standard is invoked or just a partial standard. And then sources of definition. So if there's a term used in the standard that is not defined within Y14.5, it will reference which standard that definition can be found in. For example, 1441 that we mentioned here. The use of notes is not changed. And acronyms and abbreviations, the standard does a little better job. The first time a term is used, it will be spelled out, and then thereafter, either the acronym or abbreviation will be used throughout the standard. Okay. Units of measure is not changed either. Again, figures have been updated to include 3D data in a lot of those figures. And then precedence of standards is explained a little bit better. It lists all the Y14 basic drawing standards, and then it also lists additional standards that provide additional requirements or exceptions to those basic drawing standards. And then last, the use of a Y14 case is also addressed. If there's any ambiguity and you wish to get clarity from the Y14 committee, you could submit that and get an answer, and then you would have to note that on the drawing as well. Okay. So let's talk a little bit about words used in the standard, mandatory words such as shall or recommended, guidance, and optional words or phrases. And you can see we did a little comparison here, and there's a significant increase in the word shall, so there's a lot more mandatory requirements. Basically, a lot of the requirements that were optional or used the word should have been revised to clarify that they are mandatory requirements. The word should increased a little bit by 20, may actually decreased significantly, and the phrase unless otherwise specified also increased. So that should help provide clarity as well. And then let's talk a little bit about drawings without reference. So there's a new standard. It's not really new. It was first published in 2013, the ASME PDS standard, Product Definition Specification Standard. And in that standard, it states that if there is an older drawing that doesn't have a reference to any standard at all, then you would use this standard to help provide guidance in which standards should apply to it. There is a table that lists the applicable surface metrology or measurement standards or drawing standards that were applicable at the particular date of release for a particular drawing. So you could look up the date of release and then see what particular standards would apply. In Section 2, where it discusses reference to other standards, it delineates the difference between what they consider cited standards and non-cited standards. So a cited standard is one that is considered part of the Y14.5 standard, and we list several here for examples. And then in the box on the right, we list a couple standards that are referenced, but then non-cited, in other words, not considered part of the standard. So in other words, they would address topics that are not covered in Y14.5. For instance, 14.38 would address abbreviations, and Y14.100 addresses anything that's engineering drawing related, especially requirements for notes. So the new Section 3, which is the old 1.3 in 2009, is where you'll find all the definitions, and as we state there, there's many terms that have been revised for clarity. In other words, they're grammatical changes to improve the understanding of the definition without being a technical change, and there's too many to list there, as we say. On the left here, we see there are 6 new terms, and actually the first 2 terms are really not new. It's just that they were not part of the definition section in 2009. And now they have been moved to the definition section. You have to go to the applicable section of the standard to find their definitions. The last 4 terms in blue italics are new terms that were not in the previous version of the standard. And then on the right, we list 5 terms that have been removed. You'll notice concentricity and symmetry were removed. We'll talk more about those later. And lastly, you'll notice that the term true geometric counterpart replaces the old term theoretical datum feature simulator, which we feel is an improvement because we think that the term true geometric counterpart gives a better description of the intent there, and we'll talk more about that later as well. Okay. So next, let's talk about Section 4. In that section, we'll find fundamental rules, tolerance defaults, and dimensions and practices. And the first fundamental rule that was revised is Rule A, and in that rule, it clarifies that direct plus minus or limit tolerances or dimensions only apply to size dimensions. In other words, you can't use those to locate a feature or feature of size. So the second part of that rule clarifies that geometric tolerances must be used to define basic feature definition. In other words, you must use either a position tolerance to locate a hole or a profile tolerance to locate or orient a surface, not plus-minus tolerancing. So the effects of that rule, as we see here, you may remember in the earlier versions of the standard, there was a figure that showed two shaft drawings. And one figure, like the one on the left, showed baseline dimensioning, and the one on the right showed direct dimensioning, where you directly dimension between the surfaces that were related to each other functionally. And again, since Fundamental Rule A now clarifies those are no longer allowed for locating surfaces, as we see here, they can only be used for size dimensions, or maybe corner chamfers or radii, but not to locate surfaces or features of size. So that figure was revised in the new 2018 version. So instead of showing plus-minus tolerances, it now shows basic dimensions with profile tolerances, and you'll notice the drawing on the left shows two profile tolerances with the common datum reference to be equivalent to baseline dimensioning, and the drawing on the right shows where it was redimensioned, where we're controlling the relationship between the functional surfaces directly. So the datum references have been revised accordingly to convey that, and you'll notice then we also reflect the difference in tolerance accumulation. Obviously, directly dimensioning or tolerancing between features that are related for function will reduce the tolerance accumulation. So the concept is basically the same, but obviously it's done differently now. Cannot use plus-minus tolerances to convey that. Okay. So next rule was Fundamental Rule G. That was actually split into two rules, G and H. The G part of that still states that dimensions should be arranged for optimal clarity. The H rule tells us still that on 2D drawings, dimensions should be applied to visible outlines and in true profile views for understanding, clarity. But what's new is what we see in blue italics there. It included a sentence or statement that in 3D models, dimensions shall show their true values. Okay, so in other words, they updated that to be applicable to 3D models per the 1441 standard. Fundamental Rule L was also revised. You may remember in the previous versions of the standard, or at least 2009, it told us that where we saw features that were coincident or coaxial to each other, that there was an implied basic zero as long as there was a geometric tolerance that defined the relationship between them. That is still true, but now they included CAD models in that. So if you have a queried distance between two features in a CAD model and it's zero, and there's also a geometric tolerance that defines the relationship, then it is also considered an implied zero, just as if it was on a 2D drawing. Okay. The next fundamental rule is Rule O. Okay. You may remember in 2009 there was a rule that told us that all dimensions and tolerances apply to the full length, width, and depth of the feature that it's being toleranced. And that's still true, but they expanded on that and said, well, that's also true with datum features. Datum features also apply to the full length, width, and depth of the feature, again, unless otherwise specified, like with datum targets. A new rule is Fundamental Rule Q. So this rule tells us that nominal dimensional values do not define a target for either function or manufacturing purposes, unless you state otherwise either in a note or in a reference document. So that diameter 48 is just there for, identification purposes only. It does not convey target for manufacturing like SPC or for function. Okay. And then there's also a new fundamental rule S. So this rule basically tells us that all surface elements shall be within the geometric tolerance zone. And what it does clarify for us is that it considers surface texture and flaws such as burrs and scratches to be also surface elements. So they also must be within that geometric tolerance zone. Prior to this rule, prior to this version, people had different interpretations. So does the tolerance zone include burrs and scratches or surface texture? And Many times customers would prefer to have those included, and obviously suppliers not, and so it was a source of dispute and could obviously lead to disputes in part acceptance. So now that's been settled there with this rule. So next, let's talk about Section 5. In that section, it discusses tolerancing, the interpretation of limits, limits of size, and material condition modifiers, and this was the old Section 2 in 2009. And there were several significant changes in this section. The first one being the revision to Rule Number 1. So again, since there's a lot more 3D model based definition for our products, it's telling us that 3D model geometry represents the Rule 1 boundary. Okay? And again, it's reiterating that all elements shall not violate the boundary. Okay? In other words, must be within the tolerance zone, including burrs and scratches and surface texture, as Rule S told us. Also, what it addressed is where there are localized areas that have no opposed surface elements, like we see here on the right with the flat on the shaft diameter. It's telling us that the distance between the unrelated actual mating envelope and a low point on the surface opposite shall not violate the LMC size limit. Okay, so that is a new concept there. And then also, exceptions to Rule 1 was revised. Now it includes the free state symbol and the average diameter. Okay. So as we see here on the right, we have the average diameter. So that means this part, when measuring that OD, is exempt from Rule 1. Okay. In the past, you would have to specify a restraint note, or you'd have to use the independency symbol. But now they're saying, hey, if you don't want to restrain it, you want to still measure it in the free state, and you can use the average diameter here to override basically Rule 1. So that obviously would apply to flexible parts like a large diameter with thin wall, like the one we see here, or O-rings would be another good example. Controlled radius was also revised because of its ambiguity, because people often ask the question, what is a fair curve without reversals, which is the definition of a controlled radius. So since there could be several answers to that, this standard now clarifies that a note or company or industry standard must be specified on the drawing that clearly defines the requirements of that surface. And again, that note would include surface texture and burrs or scratches or anything like that. Okay, and in most cases, probably profile and a surface texture specification would be appropriate as a better means for clarity. So next, we'll talk about two methods of interpreting such a position tolerance or other geometric tolerances that could be specified either at MMC or LMC. So most of you probably already know that when you see a position tolerance at MMC specified on a hole, for instance, the preferred interpretation is the virtual condition boundary. So when located in the datum reference frame, the surface of the hole must clear its virtual condition boundary, and that is the default condition. And this standard makes further emphasis of that, and then also further clarifies that if you do the axis interpretation, in other words, have a tolerance zone that the axis of the unrelated actual mating envelope must fit within, if there's extreme variation in form or orientation, when verifying the location of a hole, for instance, it may not have its axis fit within its tolerance zone, but its surface may still clear that virtual condition boundary. So it's further emphasizing that boundary interpretation is the preferred interpretation and takes priority over that axis interpretation if there's a discrepancy in part acceptance there. And then what is also new, it addresses applications where you may have a negative virtual condition boundary size. In other words, for example, you may have a very small hole with a large position tolerance value. And therefore, doing the calculation, your virtual condition becomes negative. And obviously we can't have that. So it just clarifies that when that happens, the surface method does not apply. Now you do have to use the axis method for verification for the location of that feature of size. Okay. And then also it added some additional verbiage there to further clarify surface and axis method interpretations for LMC as well. So on this slide we see a simple example where we have a plate with two holes, and we show both the axis tolerance zone and the virtual condition boundary that the surface of the hole has to clear. And we can see in both cases the surface does clear its virtual condition boundary, but the axis does not fit within the axis tolerance zone. So according to 2018, it's further emphasizing that these two holes will meet their position tolerance requirements specified at MMC. So that takes care of Section 5. Next, let's talk about Section 6, Symbology. Okay, and there were several changes there. Again, the most significant change, as we see looking at our chart, there's only one location tolerance position. There's no longer symmetry or concentricity. Those have been removed. So now, of course, that means there's only 12 symbols instead of 14. And another significant change to the standard is the addition of two modifying symbols. We see down there at the bottom of the right chart there, we have the dynamic profile symbol and the from to symbol both added. So we'll talk more about those later when we get to the profile section. Again, as I mentioned previously, we show an example here where the standard does show a lot more 3D model applications in many of the figures, and of course those 3D model applications will have to conform to the Y14.41 rules as well. Another significant difference in this standard is the use of the datum feature symbol with datum targets. In the past, if you had datum targets and also the datum feature symbol specified on the same datum feature, you could show them separately, but now they're saying, hey, if there is a datum feature that's identified and established using datum targets, those datum target letters and numbers must be specified next to the datum feature symbol wherever it's shown on the drawing. And it could look like either one of those two that we show you there. Another change to datum targets is their use in 3D models again. The standard further clarifies that datum target point line or area will be or shall be represented with supplemental geometry. And of course you could interrogate that geometry to query it, in other words, to know its exact location and orientation in the datum reference frame. And it's also clarifying that the use of basic dimensions for location in 3D models is optional. Okay. And the next significant change is the free state symbol. So as we see on this drawing, there's a free state symbol specified next to the size dimension. So in previous standards, it was only shown it with the geometric tolerances. Now it can be applied to size dimensions. So for this example, we see note 3 identifies a restraint note. So we're clearly identifying this as a non-rigid part that must be measured in the restrained state, but we want to exempt that size dimension from that restraint note. So of course we'd add the free state symbol. However, you do notice that the flatness feature control frame does not have the free state symbol specified, so that will have to be verified per that note 3. And then a slight change to the continuous feature symbol. That was used in 2009, but primarily the way it was defined in 2009 was it was applicable to interrupted features of size like diameters. Now in this standard, it's clarifying, well, you could have interrupted surfaces, and if you have a geometric tolerance associated with those interrupted surfaces, like this flatness tolerance we see here, you then can specify the CF symbol next to the feature control frame to convey it applies to both interrupted surfaces as if they were one surface instead of two. And also notice the 2x above the feature control frame, so you can clarify exactly how many interrupted surfaces are included in that continuous feature specification. Okay, so that's kind of an expansion on the same concept that was first introduced in 2009. So I think that's a nice addition as well. And again, I should remind everybody that we're just giving a real brief overview of many of these concepts, and we'll go into much greater detail on a lot of these in our upcoming classes that will be released in 2020. So up next, let's talk about datum reference frames. That's Section 7. That was the old Section 4 in 2009. And one of the most significant changes was the return of the old term true geometric counterpart. So many of you may be familiar with that term from the 1994 standard. And it was actually, according to my research, it goes way back, I believe, to 1996, or 1966, I should say. I found it in that standard as well. So it's been around many decades, and many people are familiar with it. And when the 2009 changed from true geometric counterpart to datum feature simulator, I think that was a source of confusion for a lot of people. So now we're back to the old tried and true term that I think most people are familiar with, and I think better conveys the concept, because in this case, where we see datum feature A is the OD of this part here. Its true geometric counterpart is a minimum circumscribed cylinder. In other words, it's its unrelated actual mating envelope. Okay, and the datum axis is the axis of that unrelated actual mating envelope. So again, I think that's a nice improvement too for clarity. And then another significant change, some of you may be familiar with the Y14.5.1-M-1994 standard. That's the standard that gives us the mathematical definitions of our geometric tolerance zones. And some of you may remember that there is a concept that's called the candidate datum set, and basically what it tells us is that if we have a datum feature that has surface irregularities, like this convex surface, you have multiple tangent planes, and each one of them is a candidate datum plane. And again, that would be its true geometric counterpart. But of course, as we show you here, that means, when setting a part up in a gauge or fixture, the part could be easily rocked or wobbled. And according to the Y14.5.1 standard, if the part can pass in any one orientation, it's considered good, it's accepted. And of course, that could lead to increased measurement uncertainty and disputes between customers and suppliers. So that was addressed in this standard. And now, 2018 tells us there's only a single solution allowed. So if we see a convex surface like this, it must be oriented to give us just one solution, where basically the gap at each end is a minimum to the true geometric counterpart, in other words, datum plane. So we're not allowed to rock it any old which way we want. There can be only one solution, and that solution has what's called the minimum separation between the datum feature and its true geometric counterpart. And the mathematical definition of that will be defined in the latest version of Y14.5.1-M. The release date, though, we don't have at this time for you. That will be determined. Next up is the calculating of an MMB boundary, max material boundary for a datum feature of size in this case. So as we see here, we have this datum feature C that has several geometric tolerances applied to it. And each of those geometric tolerances will affect its MMB calculation based on whether it's a primary, secondary, or tertiary datum reference, as we see in the chart above. And so, in 2009, they showed similar examples, but there was no straightness tolerance specified, so they only addressed position and perpendicularity and their effects on the MMB calculation. But now we see that if it's a tertiary datum or primary datum reference, that straightness tolerance will affect its MMB calculation, again, as we show you in the chart above. So that helps clarify the MMB calculations, and then they added similar examples for both LMB and RMB cases that we don't show here in this presentation. Next up is the movable datum target application. That has been clarified. So, movable datum target symbol has that little triangular pointer, which some like to call a little bird's beak. And if you read the old 2009 standard, and if you didn't read it carefully, and if you just look to the figures for examples, you could easily misinterpret the use of that symbol and think that that little pointer identified direction of movement. But in 2018, they clarify that that pointer is not a direction indicator. It does not indicate direction of movement. And it further clarifies that it can only point right or left, not up, down, or diagonally, or any other direction. Okay? So what was lacking from 2009, it didn't give good examples of how to indicate direction of movement. It just stated that if the direction of movement was not normal to the surface, then you had to clarify that direction of movement. But again, did not give you any good guidance in that. But now they gave us guidance, as in this case we see here, we could use IJK vector direction indicators to identify direction of movement. Or in a 3D model, for instance, you could use supplemental geometry like a line element that would identify direction. Okay. So that was section 7. Let's go to section 11, talk about tolerancing of profile. And so many of you may remember from the older, I believe 82 and 94 versions of the standard, you could do these phantom lines, draw those to indicate the profile tolerance zone if it wasn't equally displaced about the true profile. So in this case, we're showing a unilateral tolerance zone that applies to the outside of the surface only. And in 2009, they introduced the unequally disposed symbol. Well, now in 2018, the old method of the phantom line is no longer used, so you can now only use the unequally disposed symbol to indicate the location of that profile tolerance zone relative to the true profile. And of course, that is applies better to 3D model applications, again, model-based definition. So the next big significant change, as we see here, is where we have a composite profile tolerance in this case. And if we look closely, we'll notice in that feature control frame applied to the triangle hull, we have a little triangle symbol in the lower segment. That is called the dynamic profile symbol. And what that does, that means that lower segment only controls the form of that triangular hull, the form of its surface, not the size. The size is controlled by the upper segment. So if we did not have that symbol in that lower segment, then this feature control frame would be illegal because those two segments would be redundant. They both would control size, and of course we don't want that. So this is a way to unlock the form control from the size control and have two separate tolerances, one for size and one for form. So if we take a closer look at this in the next slide here, we see the 1.2 wide size tolerance zone, and then we see the true profile. And of course, that size tolerance zone is centered, fixed about that true profile. And then we see that much smaller 0.2 wide form tolerance zone for the dynamic tolerance zone. And the dynamic profile tolerance modifier tells us now, since that smaller zone is only controlling form, it's allowed to expand and contract within that much larger 1.2 size tolerance zone. So as we click the buttons here, got to click the right one, we see that that tolerance zone is expanding, okay, until it reaches the outer boundary of the size tolerance zone, and then it can contract until it reaches the inner boundary of that size tolerance zone, as we see there. So so in other words, it's not fixed in size. It's not fixed relative to that true profile, okay, because it's only controlling form. So again, we can take another look at that and see how that it's allowed to expand within that zone, okay. So that is the dynamic profile tolerance zone. So next up is the from-to symbol. So if we look closely beneath the feature control frame, we see an A and then a single arrowhead B. So let's not confuse that with the between point symbol where you see two arrowheads. that means that profile tolerance applies between points A and B. But here we just see just a single arrowhead. That's the new from to symbol. And we would typically use that with a non-uniform profile tolerance zone. As we see here in the feature control frame, we have two tolerance values. So basically what this is telling us is that that tolerance zone changes in width. It starts at point A and it's 0.1 wide, and it continues to point B where it's 0.3 wide, and so it can increase proportionally along that true profile from 0.1 to 0.3 between those 2 points. So it's another way of indicating a non-uniform profile tolerance zone. The method first introduced in 2009, where you just you had to draw phantom lines and dimension with basic dimensions the phantom lines on a 2D drawing or in a CAD model to describe the size and shape of the zone, is still permitted. But this is another method that you could use, and so in certain applications you may find this provides better clarity again. So next, section 12, we'll talk a little bit about runout tolerances. One of the significant changes to the runout tolerances is that you may remember in the previous versions of this standard, runout was always described in terms of the inspection method. They showed a dial indicator, and they told you that the runout controlled the deviation between high and low points, the full indicator movement of that indicator as it ran along the surface. But now, just like all other geometric tolerances, they're saying, well, no, we should be describing it in terms of a zone. So as we see here, we show total runout, and so the standard now describes it in terms of the space between two coaxial cylinders that would be centered on the datum axis, as we see here. And then it further explains that it could be applied to interrupted surfaces, as we see in this case, and it clarifies that it only applies where the surface elements apply, not where there is no surface elements. And then, of course, you could also use the CF symbol with it if you wanted to help further convey that it applies across all interrupted surfaces, just like we showed with flatness. Okay? So that provides, I believe, further clarity for description of the tolerance zone, and unrelating it from the method of inspection, because there's many good methods that could be used, or instruments could be used, such as CMMs, and not just indicators. And another significant change to runout is its application on assemblies, like in this case, electric motor shafts. You may remember from the previous versions of the standard that runout could only be applied to parts and datum features. You could only reference datum features that established an axis of rotation. And in this case, if we notice that A and B are not establishing an axis of rotation. A is the mounting surface, B are the 4 mounting holes to locate this motor. And so for shaft or for assembly applications like this, we could reference those mounting datum features in the runout tolerance. And those would be used to constrain the rotational degrees of freedom when measuring the runout of that shaft. So that's something that's really been done for a long time in industry, but was never addressed in the standard. So people that had applied runout in this types of applications often, were discussing or disputing, is this accepted or not? And now the standard addresses that and settles that dispute. So that's another good improvement, I think, too. And I hope you agree. So that kind of brings us to the end of my discussion here. Why would we want to adopt the Y14.5-2018 version of the standard? Of course, we list all the things we just discussed here briefly. And I think you might agree with me that, looking at each one of these, the reorganized content, removing of some symbols that had, disputes and so forth, and addition of some additional modifying symbols and clarification of those 3 items we list there, and of course all the non-technical edits, I think you'll agree with me that will provide more readily acceptance in industry, more easily accepted in industry. Definitely, I believe it adds clarity to the predominantly used concepts, and provides several new tools to address the applications in industry. And I believe it should improve drawing interpretation concerns and settle disputes. And so it would alleviate part acceptance disputes. And ultimately, all those should improve quality and obviously reduce product costs. And hopefully, I believe you should agree with me on that.